Hey everyone, Sin here. Welcome back to part 2 of the laser turret project in LabVIEW. In this video, as mentioned in the previous video, I'm going to show you how to write the LabVIEW code to control our 2-axis pan and tilt servo configuration and our laser turret. So if you haven't seen the first part, please do go and watch it so you get the context of what we're actually trying to achieve in this video. Now, before we write these VIs as seen on screen, the first thing we're going to need to do is upload the firmware through LabVIEW to your Arduino. Now, originally I made a video for LabVIEW 2019 on how to do this by downloading the LINX package through the VI package manager. But from 2020 onwards, the LINX, or as it's now been renamed, the Hobbyist Toolkit, is now automatically included in LabVIEW. So to upload the firmware, all we're going to do is go into Tools, go to Hobbyist, Firmware Wizard. Once that loads, you have a selection of devices. For me, it's an Arduino Uno, so I'm going to go Arduino. Arduino type is going to be an Uno. It's SubVI serial. That's the only option anyway. You can ignore the settings button, click next, select the COM port. For me, it's COM port 5. This just means what USB your Arduino is connected to. If you don't know what USB port your Arduino is connected to, in the first video I made, I showed you how to do this very clearly. A quick way to work it out is just to open the Arduino IDE and check what COM port the Arduino is connected on there, and then select that in here. Click next, leave these as default, click next. Okay, done. Once it's uploaded successfully, what you want to do is just double check the log and make sure there are no errors in here. So if there's any errors in here, there's been a problem with uploading it, because sometimes it will say it's completed, but they might not have actually uploaded the firmware correctly. Click on finish. And now that we've done that, let's create a new VI. Click on file, new VI, or you can press Ctrl N. Now we have a new VI open. This panel here is called the front panel, and the white panel or the background panel is called the block diagram. This is where you write your code, and this is where you generate your user interface. So the first thing we're going to do is right click on the block diagram, go to structures and select our while loop. Now this while loop works the same as any other while loop in any other programming languages that you use. It will keep running until you meet its loop condition, whether that's pressing the stop button, which sends a true flag to the stop condition, or there's an error in your VI, for example, and you've routed that to your loop condition as well. Okay, now that we have the while loop down, let's right click the block diagram, go to the Hobbyist palette and hit this little pin icon in the top left hand corner, which will keep it floating on screen at all times. Just move that out of the way. Then right click on the sensors icon, go to the motion icon, open servo, and then hit the little pin icon again. This should keep it on screen now at all times with the Hobbyist palette. Now these are all the functions that we need to develop our VI. Next, we're going to copy the open and close functions for the Arduino and servos respectively to the block diagram. This is for the Arduino, this is for the servo, and this is for the servo again, and this is for the Arduino. Please note the order, it's very important. We want to open the session to the Arduino first, then open a reference to the servos, then we want to close the reference to the servo, and then close the reference to the Arduino. The next thing we're going to do is wire these up. Let's highlight all of the functions, right click and show visible items label, and do that for all of them. This way we know what each function is so we don't get confused. Let's first route the wires from the open VIs to each other. So you connect the LINX resource output of the open.vi to the input of the servo open.vi, and likewise for the error wire. Then just route this to the while loop. Do the same thing for the close functions. Just ignore the broken wires for now, as we'll fix these later. Now those are wired up, we can start putting our indicators and other functions to support these. For the open.vi, right click on the serial port input and create constant. Right click on the error in and create constant. This way, whenever the VI runs, we initialize the error cluster to clear out any previous errors in the previous instance of the VI. For the COM port, I've done this as a constant because I always know what COM port my Arduino is going to be connected to, so I don't need to use it as a control. If you require it as a control because you always change your USB port for your Arduino, then that's fine too. Next, I'm going to go to the device name output and create indicator. This is a good way to see if your Visa session to the Arduino is initialized correctly. For the servo.openVI, because we're using more than one servo, we'll click on this drop down box, which shows that this VI is a polymorphic VI, and select N channels. This allows us to input more than one servo through a numeric array. We can generate that numeric array by clicking create control, and here we have it, a 2D array, which allows us to specify what channels our servos are on. If you double click on this control, you'll see it has come onto the front panel, as has our device name indicator. If you expand this in either the horizontal or vertical direction, you'll see you can generate a 2x-n dimensional array. I'm just going to have it as 2 columns, where I'll specify my servo channels as 5 and 6. So now whenever the VI runs, it will grab those two values and pass it to the servo open.vi. We will also run this wire to our while loop. Now go to the servo close.vi function and also select end channels. Right click on the error output of the close.vi and scroll down to the dialogues and use the interface palette. Then locate the simple error handler VI. And this will automatically connect to your close VI. This just simply handles any errors you encounter by putting up a pop-up dialog. And that's it for the exterior of the while loop. We can now focus on passing the pulse width values to our servos in the while loop. The next thing we're going to do is drag the servo set pulse width VI into our while loop. This is the function that will set the pulse widths of our specified servos. Connect the LINX resource and error in inputs to the left hand side and connect the outputs of this VI to the connectors on the right hand side. Now if we look at the inputs of the set servo pulse width VI function, we will see we have servo channels and pulse width. Servo channels we've already set up through our servo channel array. Now if we wire this directly to our function, it should automatically change to end channels, and it is done as you can see there. The last thing we need to input is the pulse widths. Now we need to set the pulse width for the tilt and the pan servos. To do this, we need to generate an array of two pulse width values. So we're going to go to our front panel. We're going to right click, go to Numeric, choose a vertical point slider. Do that again, but select a horizontal point slider. This will be for our tilt servo and this will be for our pan servo. We can go back to our block diagram and select these. We will rename the horizontal one pan servo and the vertical slider will be renamed tilt servo. We will then take these values and build an array. To do that, right click the block diagram, go to array and go to build array. Click on that, drag it down so you have two inputs for two elements, wire the pan, the first element, and the tilt to the second element. And now we have an array. We can now wire this to our pulse width values and we're ready to go. However, if we look at the input on the set servo pulse width function for the pulse width values, we can see there's a little red dot here. And that's because the data type of the slide controls are different from the data type this function expects. To see what data type this function expects, we can scroll down in the context help and we'll see the pulse width value is a 1D array of unsigned 16-bit integers. To simply rectify this, right click on your control, go to representation and select 16-bit unsigned word. Do this for the other control. And now you can see the red dot has disappeared. Okay, now we're pretty much done with the block diagram. The last things to do are finalize wiring up the servo.closeVI by running the servo channel array to it. So just click on that, run it to the end of the while loop, and then run that to the servo close function. And lastly, we need to wire the loop condition. Now, the way I'm going to do this is I'm going to wire the error cluster to it and also a stop button. So right click on the loop condition and create control. We have our stop button. We'll delete this wire and press Ctrl B to get rid of the broken wire. Then we'll right click on the block diagram, go to Boolean and find the OR function. This is just a logical OR. It will compare the stop button to the error cluster, which also has a Boolean value in it. And if either of these are true, it will write a true value to this loop condition and end the while loop. And that's it. The last thing to do after that is just clean up your block diagram so you have it nice and neat looking something like this. Now, if you want to generate these little labels, all you need to do is double click on the block diagram and you can start typing whatever you like. Now let's move on to finalizing the front panel. Okay, now that we've cleaned up our block diagram, there's only a few things we need to do on the front panel to get everything working. The first is to clean it up and make it look nice and pretty. And the second is to configure the range of our numeric controls to fit the pulse widths of our servos. Now for these servos, the pulse width range is between 500 to 2500 milliseconds, giving you a range of 2000 milliseconds. So the first thing we're going to do is we're going to start with getting this stop button here. Going to right click it, go visible items and click on label because I don't want to see the label of it. Drag it out to extend it. The text is a bit small, so go to your font editor here, go size, go 24, maybe a bit bigger than that, and bold as well. So let's go size, go to 36. Yeah, that looks big enough. Next, we're going to go to our servo channel control. We're going to right click on this, go to visible items and hit on index display. That'll get rid of that little control there. We can leave the label because we want to know what this actually is. We'll type 5 and 6. So that way when we run the VI, it will always load 5 and 6. If you want to set this as a default value, you can right click on it and go to data operation and make current value default. So that means whenever you load this VI, that value you've entered in there will always be the default value instead of 0, for example, or null. Device name, drag that over here. Let's rearrange that a bit. So let's put this under the stop button. Okay. Now I want to align all these, align these controls and indicators. Go up here, click on this little align objects tool, go align left edges, and you see it will align them nice and neatly. And we're going to space them out equally as well. So let's go to vertical gap, and that will spread it out nice and evenly. Drag that and put it in the corner. We have our two pan and tilt controls here. They're a bit small, so click on the little icon here, drag it out, do the same thing for the arrow. Okay, do the same thing for the pan one. Okay, now it's just a bit easier to use. Next, we need to adjust the ranges of these. So to do that, you can either double click on this and change the value, or you can right click on it, go to properties, go to scale, go to minimum range 500 and maximum range 2500. And we have the same thing there. So that's done. Now we'll just drag the front panel to fit the VI, make it more symmetrical. And finally, we can just put some decorations in order to group everything together. So I put a decoration there, I'll drag it across there, click on it, and go to, then click on the reorder button and go move to back or move backwards. That would help if I actually press it. There we go. And now we have a nice little container. You can of course customize this to whatever you like. Double click on the front panel and just type a label. So type in here general controls, drag it up a bit, scroll up, drag this up a bit, drag your label you just generated, double click on it, select all, font, go to style, put bold, size 36. And if you want this to be in the center of this decoration, just drag it to match the width of the decoration. And now when we go to our font and go to justify, click on center, and now it's in the center of the decoration. And that's how you make everything look pretty nice. And once you're done messing around with that, you should have something that looks like this. And if we run this, we'll be able to control a servo as we demonstrated in part 1. Now let's move on to the more complex VI. Okay, now that you're happy with your front panel and your block diagram, we can move on to adding in an event structure to control the servo position with our mouse and keyboard. So going back to our block diagram, just close the Hobbyist and Servo toolkits because we'll no longer need these. Bring that to center. Now we're going to expand it a bit. We're going to hold the control key and expand the while loop. And the very first thing we're going to do is right click on the block diagram, go to structure, go to event structure, and drag this around the pan and servo tilt control and build array function respectively. Because actually that's the only part we're going to add an event structure to. The next thing to do is to clean up your block diagram to make everything fit nice and neat, which is what I'll do now. And you'll notice if you press the control button again and expand the event function, it will also increase the width of the while loop and the contents inside. It's a cool trick to know. Drag out the block diagram window again to fit all the contents. Let's just clean this up a little bit more. Move this here to the right so we know it's an output. Right click on it, clean up wire so it's nice and neat. Okay, the very first thing we're going to do is right click on the case selector of the event structure. Go to events handled by this case and change the event type from a timeout to a control. So click on tilt servo and select the value change. Whenever the value changes of one of these controls, it will trigger this event case. But because we want it for both controls, we'll go to add event, go to pan servo and value change. Hit OK. And now you can see the case selector has changed to capture these two events. So if either the pan servo or tilt servo control changes value, this event case will execute. The next thing we want to do is keep track of the pulse width array that we're creating here. So whenever an event structure case executes and changes the values of this array, we want to be able to keep track of that. So as when a new event case executes, the servo doesn't go crazy or jerk randomly. And the way we're going to do that is by utilizing shift registers. So what I'm going to do is right click on the block diagram, go to array, and find the replace subset array function. Click on that. What this array does is it takes in an array and then replaces the contents of that array with a new array or a new element or subarray. So in this case, we're going to take in the previous values of our pulse width array, replace it with the new values here, and then spit it out on the side going into a shift register. And the way we're going to do that is we're going to drag these down. We're going to drag the output array to the end of the event structure. Then we're going to drag that to the end of the while loop. Then we're going to right click on it and click on replace with shift register. Now we'll click on the left side of the while loop and we'll have a matching node here. So we drag that, bring that into the event structure. We can minimize these and drag them out of the way and drag that all the way to the input side of the replace array subset function. Let's just show the label for that so we don't forget what it is and we know what's going on. Now we can delete this node, delete this wire here, delete that. We can take the output of this function outside of the event structure and run it to the servo pulse width function. Clean up wire, maybe drag this a little bit more to the right, clean up again so it's nice and neat. Stay the same, no worries. This way, the output of the event structure will always output the latest values to the set servo pulse width function, and then it will store it in the shift register. And then on the next iteration of the while loop, it will output that from the left-hand side back into the event structure to whichever event case executes. Oh, and don't forget, you need to initialize the initial values of the shift register by right-clicking on it and creating constant. This way, on the first iteration of the while loop, you don't write some gibberish values to your servos and they go crazy, as demonstrated in the first video. So I'm just going to put 1500 and 1500 as the initial values. This will set my servos approximately to 90 degrees each. And that's it for the first event structure case. Next, we're going to move on to adding an event case for the stop button. So right click on the event case selector, go to add event case, go to the stop control, and again, value change, hit OK. And now we have a new event case for the stop value change. Drag the stop control into this event, delete this wire, right click on this node here and click create constant and change that to true by clicking on it. And then press Ctrl B to get rid of the button. And as you can see, we don't have any errors in our run button. So now, whenever we change the value of our stop button, we will always write a true value to the loop condition. Make sure you pass through the pulse width array to the node on the other side. So when this event case executes, it just passes whatever the previous value was. As if you don't do it, it will just pass the default value, which is 0 or nothing. Okay, now that we're done with the easy cases of the event structure, let's work on the keyboard controls. To do this, right click on the selector label again, go to add event case, go to this VI, go to key and go to key down. This will handle all the key press events, so pressing up and down or left and right, and any other key you want to add in. Press OK. And now we have a new event case. Minimize the outputs and only leave the V key output visible. You can do that by clicking on the output and selecting V key. This output will output whichever key is pressed on the keyboard into this event case. And this is how we will determine which key has been pressed. And based on whichever key has been pressed, we will act accordingly. To move the servos up and down and left and right, we'll add a case structure to this event case. By right-clicking the block diagram, going to structures, going to case structure, and dragging that in here. We'll wire the input of the case structure to the output of V key, and now you can see it's auto-populated one event case. So we have the default, which is the ASCII case, where we will do nothing. We will drag the pulse width array through this case where nothing is done, and add a small label saying do nothing here. The other cases we want to handle are up to tilt the servo upwards, down to tilt the servo downwards, left and right to pan the servo left and right accordingly. Go to the selector label, double click on it, and type up. So now whenever the up key is pressed, it will go into this case. All we need to do here is modify tilt value to increment the servo upwards. And to do that, we're going to right click, go to array, find index array. We're going to take the input of the pulse width array and bring it into an index array function. We're going to index array 0. So this is the tilt value of the array. We're going to add 50 milliseconds to this by adding the addition function and adding a constant of 50. We're going to coerce this value by going to comparison and selecting in range coerce. All this will do is if the value increments over 2500 or decrements below 500, which is our limits, it will just coerce it to 500 or 2500, whichever is closer. This way, you don't send a value such as like 2600 to the servo, which will make it do nothing. We will take the output of this and we will add it back to the array by going to array, replace subset, passing the pulse width array into it, passing the output of the coerce function into the input of replace array subset function, and again, we'll index it at 0. The index of 0 is where the tilt value is located in the array, and we'll send this to the output here. Now, I want to repeat this for the down function. So I'm going to right click, select duplicate case, and it's automatically gone to down. Except now I'm going to right click on the add function and click replace, numeric palette, and subtract. So now whenever you press the down button, it will subtract 50 milliseconds from the pulse width value in the pulse width array. So whenever you press up, it will add 50 milliseconds to the pulse width array for the tilt value. Just replicate this for left and right. So let's duplicate this again. Again, it has now automatically gone left, but we want to change the index to 1, and we'll duplicate this again. But let's go to the down function and we'll duplicate this case. And now it's going right. We'll again index by 1. Just note, we want right to increment and left to decrement, but that's personal preference. But for me, that makes sense. So I'm going to replace this with the addition function, go to the left case, and replace that with the subtraction function. So now when you press left, it will subtract 50 milliseconds. And when you press right, it will add 50 milliseconds. And I completely forgot, you actually need to add the upper and lower limits to the coerce function. So right click on that, create constant, type in 2500 and do that for the lower limit, which is 500. And then just repeat that for the rest of these. And that's it for the key down press event. Let's move on to holding a key continuously. Now, just quickly before we move on to the next step, how do you actually test if this event structure is working or this event case is working? You can just add a simple debug indicator on your front panel. So right click on the V key output and create indicator. You can see it comes up on the front panel. So if we go back to the front panel and drag that here, and let's just drag that down and rename that debug. Now, if I run this VI, we get the Arduino name in the device name indicator. So the connection is established correctly. Don't worry about the servo channels. I just want to test the event case for the arrow keys. So now if I press up, it should show up. If I press left, it'll go left, right, down. So now I know that my event cases are working correctly. If I press stop also, it will stop the VI, and it stops as we expect. And that's how you debug your event cases. Very simple, don't overcomplicate it. Okay, now that we've debugged that and we've shown that it works, let's delete that indicator. Now the next case we're going to work on is the case where you hold down a key. So instead of pressing the up key multiple times to increment the servo, what if you just want to hold it down to get a smooth motion? There's an event for that, and to add it in, simply right click on the event selector case, go to duplicate this event case, go to this VI, go to key again, and go to key repeat. Now it will duplicate this event case for the key repeat event. So whenever you hold down the up key, left key, right key, or down key, it will increment or decrement the servo position in the pan and tilt direction respectively. And that's it. Now we can move on to the final case, which is the case of controlling the servo with our mouse. Okay, now in the last case, we want to translate our mouse cursor position to a servo position. So if we move the mouse upwards, we want to tilt the servo upwards. If we move it downwards, we want to tilt it downwards. If we move it left and right, we want to pan left and right. Now, how do you actually do that? We need to somehow transform our mouse coordinates into our servo positions. And I'm not going to go into the maths behind that. There are plenty of resources on how to do 2D transformations. I'm just going to show you how to set up the event case and how I do it in this VI. And I'll let you study the linear algebra for yourself. So the way I'm going to do this is by using a 2D picture control. You don't have to use a 2D picture control. You can use the mouse position on the front panel, but it's a bit easier to do it with a control. So I pull down the front panel and extend it here. Right click on the front panel, go to graph and go to 2D picture. And I put that on the front panel. I'm going to drag that out here and just drag it all the way down. Now, if I move my mouse cursor anywhere in here, I want the servo to translate directly. So if I move it up, it's going to move up. If it's going to move down, it's going to move down. If I move left or right, it's going to move left or right. Now I'm going to specify the origin to be the corner of this picture. You can obviously change that to be the center if you'd like. But for the sake of this example, I'll just start from the corner because it's easier to do. Now that we have this on screen, let's go back to our event case. Let's right click, go to tilt and servo, pan and servo. Let's duplicate this case. Go to duplicate event case, go to 2D picture, and then we're going to go to mouse, and then we're going to go to mouse move. So whenever the mouse moves, actually, hold on, just delete these controls first. Bam, press Control B. Those are deleted. Let's just minimize these. So now it's nice and clean. And here we're going to input our new servo positions that are going to be translated from our mouse X and Y coordinates. Now, as I was saying before, whenever the mouse moves inside this 2D picture, it's going to translate the X and Y coordinates in this picture to a servo position. So all you need to do is you need to map the X and Y position from the mouse cursor to a servo position. So that's pretty easy to do. You just need to do a linear fit, the X coordinates to the pan servo and the Y coordinates to the tilt servo. So how do we get the mouse X and Y cursor positions? To do that, we're going to get this picture control, drag it into our event. We're going to right click on it, go to create, property node, and then we're going to get mouse. We're going to drag that in. We're going to go to cluster, unbundle by name. We're going to connect it to our mouse property node. We're going to select mouse position. And now if we unbundle that to go to unbundle by name again, you'll see we'll get the mouse X and Y position. As I mentioned earlier, the origin of the coordinates for the mouse position are going to start at 0, 0 here in the top left corner. And it's going to be the extremities in the bottom right hand corner. So I'm going to use these values to translate into the servo positions by using a linear fit. So all you need to do is find the length and width of the picture area. Then you need to fit those boundaries to the servo positions. So you know that the maximum tilt value is going to be 2500 and the minimum is going to be 500. And you also know what the boundaries of your 2D picture control are going to be. To work those out, you can just right click, go to properties and look at the height and width. And if you want to be more accurate, you can right click again on the 2D picture control, go to create, go to property node, go draw area size, and look at what the output of this is going to be. And whatever this tells you as the width and height of your draw position, you can use to fit your function to. Now, here's something I prepared earlier. This is the finalized VI. The only difference is now I've populated the mouse move event. I'm doing all my calculations in this SubVI called map coordinate SubVI. And I'll go over how that works briefly, and I'll show you how to create your own SubVI. So what's going to happen is when I run this VI, as I move my mouse in this picture control, as I mentioned before, that will translate to a servo position, whether that's a pan or tilt or both. And the way we do that is, as we showed before, so this is just the front panel of my SubVI, and this is the block diagram. We get the mouse position in, we unbundle the X and Y coordinates. I then change them into a double float to do the calculations. These get multiplied by a gradient. Now these gradients are calculated from the origins. So we have X and Y 0, 0, so the origin of the 2D picture, which is 0, 0. Then we have the height and width of the 2D picture. And then we have the minimum and maximum pulse width values. So 500 and 2500. We want to map these coordinates to this coordinate. So what does that mean? I want to map 0 to 330 to 500 to 2500. And I want to map 0 to 582 to 500 to 2500. This just indexes all the arrays out because this is a 2D array. So I'm separating them all out so I can work on them. I'm then using the linear fit function to determine the gradient and the intercept of these linear fits. So the first one does the Y values, so the tilt values that is, and then the second linear fit function does the pan values. And as you can see here, it's just basic linear algebra. We have tilt equals M1 times Y plus B. So our gradient times our Y coordinate plus our intercept. And then I bundle that back up into an array, which is our pulse width array, and I pass that back to our replace array subset function, which just then updates the position of the servo. And that is pretty much it. Once you've done that and you've got it moving the way you want, you can control it very easily with your mouse. Now just quickly on how to create a SubVI. If you want to create a SubVI, just highlight the functions in your block diagram and then go to edit and create SubVI. And as you can see, it bundles in automatically. So if I undo that and don't save and go back to my SubVI, then you will get something like this, which will have all your functions inside and it'll pass in your references, etc. Then you click on here to set your inputs and outputs. So we have one input and one output. And then you double click on the icon and you can edit it to whatever you like. It's always nice to color code the top and then give a nice graphic indicator of what the function does and also a label preferably. And then your SubVI is done. So thanks for watching my tutorial. If you enjoy this new live commentary style of LabVIEW tutorial, please let me know. Thanks for watching, and please don't forget to subscribe and like this video if you enjoyed it. See you next time.